Professor Cummings, and we have another video, and this time it is Module 4, Lecture 3. We're still going over lean tools. So this is lean tools and how to address actual waste when dealing with Lean Six Sigma. Now, like any other type of waste and any type of thing dealing with lean, everything starts with your value stream map. So in this particular one, it actually shows a lot more how that value stream map is going to interplay with being able to address waste in this particular case. So again, to remember, and this is a slide from Lecture 1, about developing your value stream map. All a value stream map is a graphical representation of a process that shows sequence and key metrics so that waste is easily identifiable. And what I'm going to show you in this particular video is how this value stream map is going to become a crucial part of establishing whether a particular activity is indeed waste and to what degree it is waste and how you can deal with it. And in order to apply what we're going to go over in this video, you actually do need to understand value stream maps. So in order to move any further, go back and review that particular video on value stream mapping and how they're built and what actually goes into it, and this will actually help you digest this information a little bit better. So keep in mind, this is all going to be based around the idea that you can use a value stream map and understand what value stream mapping actually is. So look at this particular scenario, and I'm sure most people have seen this little clip. It's just a picture of a series of little bears waiting in two different queues, and obviously the bear in red is trying to get into the shortest queue to understand whatever it is they're trying to achieve when they meet the bear at the front of the line. And it just seems like you can never really come up with the shortest queue to get into. Now again, this is supposed to be a funny little cartoon kind of depicting, the frustrations of everyday life, making a decision, and also the alternate decision is the better one. But I like this one because it actually shows what we're going to be talking about in this particular video when it comes to lean. So as you look at this video, I want you to keep a few things in mind. Number one, think of each one of those bears either as a customer or as a work in process. And we'll give him a variable L. All right, so what's going on with him in terms of each one of those representing a customer or a work in process? So something that this business has to address. Also keep in mind that there's an average wait time, regardless of how fast or slow the line starts to move up and all the stutters and stop. There's actually an average wait time that each bear is sitting in that queue. So that we'll call that variable W. And then the last thing of these three key variables I want you to keep track of is how fast do the bears actually enter into the process. So how fast do they show up, and we'll call that lambda. So keep that in mind as we go through the rest of this video, that you've got a series of bears waiting in line, an average number of bears that are actually waiting in line, an average number of customers, an average number of work. There's an average amount of time that bear waits. If we were just to randomly pick a bear and set a stopwatch to this GIF, there would be a certain amount of time that it takes for them to actually get through that system. And we could actually calculate that through in just like any type of a process, as well as how quickly do these bears actually show up. How fast are they showing up onto the screen? Again, right at certain times it takes a while. Sometimes quite a few show up out of nowhere, but that actually can be averaged out. And you can actually put a number to that. So all these things could actually have a number. If you look through the video, and just cycle the video, you can actually come up with an interval of time and answer all three of those and have three different numbers. So a work in process, how many bears are actually in line on average for that length of the video, the average time that they're waiting, and how fast they're actually showing up onto the scene. Those are going to be key to keep in mind. So when you look at this video, I want you to ask yourself the usual question that you always ask in this particular module, Module 4. What kind of waste are being experienced by these customers? Particularly think of the bear in red. Exactly what kind of waste are we looking at? Now in Lean, we went over 7 types of muda, 7 types of waste that is actually being addressed when you apply Lean tools. And is there any way that you can quantify this waste? Again, remember, Lean Six Sigma is data driven. So how can we try to come up with a way to quantify this data so that we can actually put it into some use when we come up with a solution to it? So the different types of waste that you are witnessing here, obviously waiting is probably the biggest one. How long it takes to get through this system. And then of course there's all sorts of things like the amount of inventory into the system, inventory in this case being the number of customers or the amount of product in line, the potential for overproduction, maybe not in this particular scene, but how fast it's actually coming into how fast the bears are actually entering into the scene could be a sign of overproduction. And then, along with that could be any type of transportation costs of the bears coming in, or in this case, some sort of inventory coming in. So again, so you can start to look at this with your lean glasses on and actually see where the waste is coming in and how you start thinking of ways that you might want to address it. But before you get there, let's investigate this whole concept, this entire phenomena of bears in the queue a little bit more. So in order to understand it, we got to understand a guy named Professor John D.C. Little at MIT, Massachusetts Institute of Technology. This guy has studied process flow for decades. He was born in 1928. I think he just turned 90 years old in February, so he's still working at MIT. And that's what he's been doing. He's actually an accomplished author. He wrote 3 books: Models and Managers, The Concept of Decision Calculus, Decision Support Systems for Marketing Managers, and Brand Aid, an Online Marketing Mix Model. So he's done a lot of models for how processes flow, how queues work, and how to keep systems moving smoothly. That's what his big research is. So his research, a lot of it was dealt with traffic control, queue management, and he actually developed something that you guys, and I've been avoiding saying the name of it, for the length of this video so far. He developed something called Little's Law back in 1961. Again, if you remember all of the other videos when a lot of these dates on Lean and Six Sigma started really taking shape, you can see the 1961 is an actual very significant window of time that he came up with Little's Law. So let's understand a little bit more about Little's Law. Little's Law by somebody who spent their life understanding how things flow, how queues work, and how to manage those types of queues. All right, so Little's Law. So here's the law that Professor Little came up with, that the average number of customers in a system over some interval is equal to the average arrival rate, so how fast they're coming in every day, week, month, year, however that is, multiplied by their average time in the system. Okay, so the average number of customers in the system is equal to the average their average arrival rate multiplied by their average time in the system. When you think about that, it really makes sense. Now, when Little's Law first came out, or when this was first being used, this was being applied to, say, store owners. So how long it takes for your customer who's coming into the store to get serviced, much like the video that we saw. But this can also be applied to a manufacturing setting, can be applied to an office setting, can apply to even a hospital type setting, people waiting in the emergency room, waiting to be waited on. So in all those cases, the customer, the work in process, whatever it is that's actually waiting or actually being waiting to get your value added to it, if you have the average amount sitting in that queue is equal to the how fast they're coming in, the rate that they're coming in, multiplied by how long they have to sit. That's all Little's Law is saying. And you can represent this mathematically with this equation here. L equals gamma or lambda times W, or you can look at it in terms of W equals L over lambda. And just to clarify, L is the average number of items within the system. So that could be the items could be customers, items could be work in process. Lambda would be the average arrival rate. Orders per day, customers per week, orders per month. So you're looking at a rate, so something per unit time, and then the average wait time in the system. So if you've got customers leaving in terms of minutes, in terms of days, or something sitting in a queue for weeks or a month, That's applied by Little's law. Now, there's a few things to consider with these laws, and they're both basically, the same mathematical equation. Just one is solved for work in process over on the left, and on the right it's solved by for wait time. The average wait time you're going to have for your item. Thing to keep in mind with Little's law is a couple of things. Number one, there are 3 variables that you have some type of control over. The number of items that you keep within the system, the number of people you let in the store, the number of work in process you have on your factory floor, how fast you have them coming in, something else you can try to control, and then the last one is how long they're into the system. So some kind of way of addressing how long they actually are being processed. And this is the data that you're using to be able to make your decision. And this is also how you can quantify your waste. Like we said, the equation on the right is broken down by wait time, and waiting is a form of waste. So now you can actually calculate that wait time and put a number to it and decide how you can address it for the customer. So using Little's law, you can actually decide, okay, is parts sitting on my plant floor way too long? And if so, what can I do about it? I can either look at the average number of items I have on the system, or I can look at how fast I'm allowing these parts to be to show up in the system. But somehow I've got to be able to calculate and change, or maybe not change, that wait time. So again, one thing that's different about Little's law versus other things that fall under Lean's tool is this one is more of a way of making a decision, more so than just simply addressing a problem. It allows you to put a number to a problem, and this can be used in conjunction with other Lean tools such as Pool Systems and Kanban. So again, this is integral to a value stream map using Little's law, and the main reason is because, like we went over with value stream maps in module 1, is that value stream maps not only show the flow of the product going through your process, but also it gives you the key data, key metrics that go along with this process. So you can see here exactly how much time is being utilized at each particular part of the operation, as well as how often they're shipping and how often you've got them coming in. So you can actually put a lot of numbers to it. So let's make this more relevant to our earlier example. So if we consider that these are each bears in a queue trying to get to some particular ends, now you can actually start to consider how long you've got these bears waiting in the queue, work in process, how fast the bears are actually showing up during that particular interval of time, and how long they're actually waiting during that interval of time. And you can start to apply Little's law to this process. If you look at that window of time that GIF takes place, and actually consider how many bears are in that line, how fast they're showing up, and how long that each one of those bears wait, you can actually start to devising plans on how to address the waste that might be going on in that process. And again, you need a value stream map in order to do this effectively. You're actually using the data to try and understand the waste inside of this system. So again, just thinking about Little's law, thinking about what that is, that equation, how could you actually start to address what you saw here? Well, we look at Little's law, look at the equation of Little's law, L equals lambda times W. Well, we got 3 variables we can address, and one we can try to address the wait time. Why are these bears actually sitting there? Is there some way we can try and speed up that process, lower the wait time? Well, one thing we could do, we could actually add another person to this, or add a new piece of equipment, get more people trained in order to do this particular job. So again, with a third bear there, or a third clerk there to help work on the bears, you can actually theoretically speed up the process and reduce your wait time. So increase the capacity to perform work. Another thing you could do that I couldn't show in an animation is investigate the superfluous activities that are going on. We don't know what those bears are doing. Why do each one of those bears have to take the time that they take? And why is it some bears seem to clearly take longer than others? So if we can actually address what's going on at those stations, then we can actually reduce the wait time. And again, addressing one of the three variables in Little's Law. Another way we could get around this, looking at Little's Law, is look at how fast the bears are showing up. Why are they showing up so fast? Or why are they showing up at the rate that they are showing up? How can we address this? Well, we can start to regulate how the customers are coming in, or how many orders we take from the customer. Now, why would we want to do this? Well, maybe there's certain issues with it. Maybe we're taking too many orders that don't necessarily meet our specialty. Maybe there's things that we could actually try to address to actually keep the process a little more streamlined. Are we doing too much? Are we, trying to handle things that aren't really in our bailiwick, in our wheelhouse? So in other words, just trying to restrict the number of orders that are coming in from the customer. Another way of dealing with this, is to look at how much work in process we have. Again, this is something that you'll see a lot in manufacturing. What do we have on the floor, and why is there so much inventory on the floor? Is there some way of actually reducing that? So what if we reduce the number of bears that we have to where you're only allowed to have 2 bears in the system at any time? Now, this looks similar to restricting the customer, and it is, but we're going a different route on this one. Restrict the amount of inventory actually onto the system. In other words, implementing something known as a pull system, which you saw in a previous lecture. So again, you've got 3 variables here when you deal with Little's Law, and you have control over those 3 variables. You're able to actually calculate, what the actual wait time is based on Little's Law, based on how fast you're getting inventory in, as well as what you have on your shop floor at any given amount of time. And from there, you can actually implement other lean tools. So again, this is just one more way of addressing waste, on your shop floor. And this is just a brief explanation of Little's Law. Again, this is Professor Cummings. Thank you for watching this video, and I hope you enjoy the rest of this particular course.